This is Unit 3, Video 3, Electron Configuration. Now that we know the quantum numbers and how they reflect the electrons in the atom, we want to kind of sum it up into what is the configuration of the electron. We should be able to pick an atom on the periodic table, say chromium, and determine the configuration of the electrons inside of a chromium atom. Now we call this the ground state configuration. That's the lowest energy state the atom possibly can take on. There are definitely excited states. Electrons will move between one orbital to another orbital. And that jumping around happens all the time as energy interacts with the atom. But we're interested in and focusing on the ground state at this point. Now, the challenge of determining the configuration of the electron is knowing the energy orbital of the shell-subshell combination, or as I've said, sometimes called the energy level sublevel combination. So that's our 1s, 2s, 2p, 3s. What is going to be the order of filling for the electron? That's the challenge, it really is. You'll be able to learn pretty quickly. You know your L values of 0, 1, 2, and 3 represent s, p, d, and f. So there are s, p, d, and f orbitals available in each of the shells. Now obviously the first energy level, the first shell, can only have an s because L equals 0 is the only possible value. The second can only have an s and p. The third can only have s, p, and d. The fourth then can have s, p, d, and f, and we can move on from there. Now there are no electrons in the ground state on any atom on the periodic table that moves beyond L equals 3 to L equals 4. We call that the G subshell. So we're not even going to talk about that at this point. So what we need to know is that order of filling. That's the key. So here's my periodic table, and I can block out the periodic table very nicely now. This is my S block, only 2 electrons because there's only 1 orbital. This is my P block, 6 electrons because there's 3 orbitals. You know every orbital can hold 2 electrons with opposite spin. So I have 6 here in the P block. The center has 10, that's my D block. So this is my D block, and there's 5 orbitals, 2 electrons per orbital, that's 10 electrons. The F block has been pulled out of this spot right here. So this is the missing spot, that's where our F goes. And so F will have 14 going across here because there's 7 orbitals, each holding 2 electrons. So the question is going to be the order. Now I'm just going to run through the order real quick here. Notice the first row only has 2 atoms. That's because the 1s can only hold 2 electrons. So that's our 1s. Then our 2s. Then the 2p. Then the 3s. Then the 3p. Then, notice, we don't have a 3d. We go to the 4s. 4s. Then the 3d. So you've got to be aware the 3d is happening on the 4th row of the periodic table. 4th row because it's the 4th shell of electrons. Then we have the 4p, then the 5s, then the 4d, then the 5p, then the 6s, then the 6s we go to the 4f, then we have the 5d, and the 6p, and that's as far as I'm going to go. But you get the gist there. There's an order of filling that is not necessarily shell-subshell combination or energy level sublevel combination. So what's one way we can know that? We use the Aufbau chart. The Aufbau chart gives us a good representation of the order of filling. So here I've drawn up the Aufbau chart for us. We follow the arrows from tail to tip. So the 1s, then the 2s, 2p, 3s, 3p, 4s. This is key. We've got to know the 4s is filled with electrons before the 3d. It's actually lower energy than 3d. We're very, very close, very close. So 4s, then the 3d, 4p, 5s, and we can go all the way through. So let's do a couple of atoms. Let's start with something simple like aluminum. Aluminum, we know on the periodic table, has 13 electrons. 13 electrons starting at the 1s. So 1s2. Then after the 1s comes the 2s. 2s2. Then comes the 2p. Now the 2p can only hold 6 electrons. We know that. That's what the p block is. 3 orbitals, 6 electrons. 2p6. At that point, I've done 10 electrons. Aluminum has 13 electrons. So I'm going to go to the 3s. 3s holds 2 electrons, and then the 3p holds 1 electron. The sum of the exponents here should equal the number of electrons. So this is Bohr's principal quantum number in L, okay, the angular quantum number, and then our number of electrons found inside of the subshell. Let's do another one. Let's do cobalt. Cobalt is number 27 on the periodic table. So a neutral atom of cobalt has 27 electrons. We know that. And we'll talk about positive states and negative states later. So we have 27 possible electrons. Cobalt's obviously going to start in the 1s. So we're going to go 1s2, then the 2s, 2s2, then the 2p, 2p6. Now let's go back to the all chart for a second and just look back over. 1s, 2s, 2p, 3s. So after the 2p comes the 3s, then the 3p, then the 4s. So we're going to go to the 3s, 3s2. Then we're going to add the 3p, 3p6. At that point, I've represented 18 electrons. Cobalt has 27 electrons, so I have 9 electrons remaining. After the 3p is not the 3d, it's the 4s. So I've got 4s2. That gives me 20 electrons. I need 7 more. The 3d, d has 5 orbitals, so it can hold 10 electrons, but there's only 7 here. So we're going to finish with 3d7.